This is a pretty long question, so we'll do it in parts. I like this question though because it's a real good recap of more or less everything that's important about chapter 24. So let's read it first and draw a picture. A long insulating cylinder has a radius of 5 centimeters. So this is a long insulating cylinder. It's got radius 5 centimeters. This insulator has a uniform charge density, rho equals 3 times 10 to the minus 4, or 300 microcoulombs per cubic meter. And that's a volume charge density, it's charge over volume. The insulator is concentric with a conducting cylindrical shell. Okay, so that means there's a cylindrical shell. So this picture like an iron core, and outside of it is, oh, I don't know, like a Coke can, but the Coke can has thick walls. Okay, so there's one part of my conducting cylinder. There's the other part. That's the outer shell? Yeah, outer shell. No, I'll make this the outer shell. Outer shell and inner shell. A little bit hard to draw 3D. Okay, hopefully you're getting the idea. So this is a conductor, this part right here. This white stuff, that's just vacuum. So this is a conductor. The conductor has net charge per unit length, so this is a linear charge density. Lambda equals minus 4.25 microcoulombs per meter. The dimensions of our conducting cylinder are an inner radius of Ri and an outer radius of Ro. Okay, there's our setup and our geometry. First thing we're asked to find is the inner and outer surface charge densities on the conductor. So if our insulator has positive charges, let's think about what happens to the conductor. On the conductor, charge is free to move around. That's what makes a conductor a conductor. If this insulator has positive charge, negative charge is going to be drawn to the inner surface of the conductor because it's attracted to the positive charges on the insulator. So what we want to do to find the charge density is let's figure out how much charge is drawn to this inner surface. We'll take the charge and divide it by the area, and we'll get the charge density on the inner surface of that conductor. So that's our strategy. So part A, the inner charge density, so it's a surface area density, so surface charge density has symbol of sigma, is sigma inside, so I for inside, is the net charge on the inner surface of the conductor divided by the area of the inner surface of the conductor. Real quick sketch, there's our insulating cylinder, there's our conducting shell. So whatever charge is on that inner surface of the conductor. Sometimes it helps to draw a two-dimensional picture. So there's our insulator. This is our conducting shell. So the insulator has positive charges. That tells us that we know there are going to be negative charges attracted to the inner surface, and the net amount of charge on that inner surface we're going to call Qi. Okay, the way we're going to solve this is let's apply Gauss's law. If we want to apply Gauss's law, let's draw a Gaussian surface. Okay, Qi equals charge on inner surface of conductor. We're going to find this value of Qi using Gauss's law, and Ai equals area of inner surface. That's easy. Area is the area of the inner surface of that cylinder, 2 pi radius times the length. Okay, So if we're going to solve this, let's draw a Gaussian surface inside the conducting shell. I'll draw that with a dotted line. So my Gaussian surface is going to be a cylinder completely within that conducting shell. Okay, there's my 3D version, there's my 2D version. Gaussian surface is cylindrical shell or a cylinder inside the conducting shell. Okay, so if I've picked my Gaussian surface, I'm thinking about charge, I'm going to write down Gauss's law next. Integral of E dot dA is the net electric flux through any surface, any Gaussian surface, equals the charge enclosed by the surface divided by epsilon naught. Now here's where the part about the properties of a conductor in electrostatic equilibrium come in. What we know for a conductor in electrostatic equilibrium is the electric field equals 0. So if my electric field inside my conductor is 0, and we do know that it's 0, that means that the net charge enclosed by my Gaussian surface has to be 0. Okay, let's figure that out. So Q enclosed is my net charge enclosed by Gaussian surface. And GS for Gaussian surface. So Q enclosed is my net charge enclosed by the Gaussian surface. What charge is enclosed by my Gaussian surface? Well, let's look and see what's inside that cylinder. Things with charge. The things with charge inside this pink dotted line is the inner surface of my conductor. So that's there, that has a charge on it, and my cylinder. So my Q enclosed equals charge on the inner surface of the cylinder plus charge on the insulator. Okay, so that's the idea. Let's see what we've got in symbols. Well, charge on the inner surface of the conducting cylinder, I called that Qi. Charge on my insulator, right now for the moment, I'm going to call that QINS. Let's see if I can figure out what that is. Q of my insulator equals density of the insulator times the volume of the insulator. Density of the insulator is given as 300 microcoulombs per cubic meter. And the volume of my insulator is pi times the radius of the insulator squared times its length. Okay, that's going in for my Q insulator. My Q enclosed is 0. I'm going to solve for Qi. So 0 equals Qi plus rho times pi times r squared L. Qi equals minus rho pi r squared L. Let's put my numbers in here. Rho is 300 times 10 to the minus 6 coulombs per meter cubed times r, that was 5 centimeters, 0.05 meters squared, times the length L is not something I know, so I'm just going to leave that as an L. Oh, and I dropped my pi times pi equals 300 exponent minus 6 times 0.05 squared times pi equals minus 2.356 times 10 to the minus 6 times the length. So that's the net charge on the inner surface of my conductor. Remember, I'm asked for the charge density, which is that charge divided by the area. And I know that my area is 2 pi r times L. Okay, let's do that step next. So my charge density on the inner surface of the conductor is the charge on the inner surface divided by the area of the inner surface equals minus 2.356 times 10 to the minus 6 L divided by the area of my inner surface, which is 2 pi times the radius of the inner surface. The radius of the inner surface was given as 7.5 centimeters times the length L. Okay, there's an L on top and bottom, so they cancel. So I'll take my charge divided by 2 divided by pi and divide that by the radius. And what I get is minus 5.0 times 10 to the minus 6 coulombs over meters squared. Yeah, coulombs over meters here. Okay, so there's my charge density on the inner surface of my conductor. The question also asks for the charge density on the outer surface. So let's see about figuring that part next. So on the outer surface, the charge density of the outer surface is the charge of the outer surface divided by the area of the outer surface. And the area of the outer surface is going to be 2 pi times r times the radius of the outer surface times the length. So let's see if we can sort out what is the charge on the outer surface. So there's our insulator. There's our conducting shell. And now we're asking, what is the charge out here on the outer surface? Because we know charge has to be on the surfaces of a conductor. So how much is on that outer surface? We already know this is how much is on the inner surface. Well, what we know is that the net charge on the conductor is whatever charge is on the outer surface plus whatever charge is on the inner surface. So we've got Qi on the inner surface, Qo on the outer surface. Add those two guys together and you have to get the total charge on the insulator. On the conductor, sorry. So let's see what we've got here. So my QC, my charge on my conductor, that's going to be my charge density times the length of the conductor. And I do know the charge density, minus 4.25 microcoulombs per meter. My charge on my outer surface is what I'm trying to figure out, and my charge on my inner surface, let's just grab that sheet of paper. Where did I find that guy? There's my charge on my inner surface. So now let's solve for my charge on the outer surface. Charge on the outer surface is the net charge, take away whatever is on the inner surface. So I've got lambda L minus 2.356 times 10 to the minus 6 L. That lambda is equal to minus 4.25 times 10 to the minus 6 coulombs per meter. That guy was coulombs per meter. So that's L outside of minus 4.25 exponent minus 6. Minus a minus gives us a plus. 2.356 exponent minus 6. Minus 1.894 times 10 to the minus 6 coulombs per meter. Okay, so now I want to put this in for my charge, this in for my area, and then we'll have our charge density. So Sigma O, our charge density on the outer surface, is the charge on the outer surface divided by the area of the inner surface. L times minus 1.894 times 10 to the minus 6 coulombs per meter divided by 2 pi times the radius. That radius was given as 8 centimeters times the length L. Those lengths cancel. And when we do that through the calculator, what we get is minus 3.77 times 10 to the minus 6 coulombs per meter squared. Okay, there's part A done. There's the charge density on the inner and outer surface. I think I'll move to a new video before I do part B.